So in backtracking, we have to make series of decisions actually. Means while you're solving the problem, in each again we are solving the problem in stepwise as we did it in the greedy technique. Okay, so here we have to make a series of decisions. So among the various choices, we have to choose which one is the correct choice. Okay, we are here. You don't have enough information to know about what to choose. Okay, so each decision or each choice what you're taking will lead to a new set of choices. Okay, those some sequence of choices may be a solution or may not be a solution to your problem. Suppose if it is a solution, then you reach the goal. If it is not a solution, usually till now, if it is not a solution, we have terminated that path. But what backtracking is doing now, if you feel the path what you are following to search a goal node or a search a goal or a search a solution to the problem is not a solution, then you terminate that path and backtrack to your previous stage or previous step. In the previous step, make another decision or take another choice, okay, and continue solving the problem. While you're continuing this path, again you may reach to the goal or you may get a solution or may not be. So if you get a solution, fine, you report the solution and stop the algorithm. If it is not a solution, again go back. Means backtracking to the previous decision what you have taken in the previous step. So in the previous step, again we have to change your decision and continue solving the problem. So I hope the general plan of backtracking is clear now. If it is not clear, I will explain you that plan with examples. So then you may get a clear idea about the backtracking algorithm design technique. Okay. If you have any doubts at the end of the presentation, I will give you some time there. Then you can ask the doubt, or you can post the queries or issues in the Google Classroom. Also, I will answer all those queries. Okay. So backtracking is a methodical way of trying out various sequences of decisions until you find one that works. Okay, this is what the one-line definition for the backtracking. So now let me explain the concept of backtracking with an animation I have created. Definitely with this animation, you can understand the general plan of backtracking. Now I want to solve the given problem. So this is my starting step, first step. So I'm going to make some decision or choice. Okay, that's what the question. What I need to decide. Okay, I have decided. Okay, let me to go in right direction. I mean, here you can. It is in the horizontal, so upward. Okay, let me to move in the upward direction. So I reach to one more stage. There again, I need to make the decision. Okay, again go. Just explore that. Explore your current path. Okay, move to the next stage. And once you move to the next stage, so here you are observing it, there is a dead end. So dead end means the place where you are not able to get the solution to the given problem. So that path, that stage is called as a dead end stage. So if you are not able to make any correct decision, then it is a dead end stage. Okay, so whenever you reach the dead end stage, backtrack, go back to the previous stage and make the choices. So go back to the previous stage, and in the previous stage you have taken one decision, no? So change the decision now. Change the decision, okay, and take another decision. Continue the path. Again, you may reach the dead end. Whenever you reach the dead end, backtrack to the previous stage. And here I had only two choices. So both the choices are over. So I need to go back to my very first stage. Okay, that is just after start. Okay, so again make another decision here. Continue another decision. Continue. It's may I hope this path may lead to the goal. Okay, continue. Now even after taking three decisions, I'm not able to reach the goal node. So this is called dead end. Backtrack to the previous stage, make another decision. It is all, it may not be with the goal node. Backtrack, backtrack, Now take another decision. Take another decision. Again dead end. Backtrack. Okay, now it is success. We reach the goal node. I hope the concept of backtracking is clear now. So it's very simple. Problem is solved in stepwise. In every step, you have to make the decisions. The decision may lead to the goal or may not be. If it is not leading to the goal, and if you don't have any more choices to make the decisions, then call it as a dead end node. Whenever you reach the dead end, backtrack to previous stage, change your decisions. Okay. Once you reach to the success, the goal node, you report the message success and stop the algorithm. This is what the general plan of backtracking. Okay. So, but you may have a doubt. It is almost same as in greedy technique also. No, in greedy technique also we have solved the problem in stepwise. But there, once the choice was made, the choice was not altered in the next stages in the greedy technique. But in backtracking, yes, it is allowed to make your change. You can change your the decisions what you have taken in the previous stages. So this is a very good animation to explain the concept of backtracking. So now let me to explain some terminologies I am going to use in my explanation. Okay, the terminologies are first the tree what you have seen in the previous slide. No, it's called as a state space tree. Yeah. Okay, it is composed of nodes. You can observe here nodes, and there are three kinds of nodes here. One is the root node. In green color it is there, and internal nodes are there, and leaf nodes are there. Okay, so backtracking can be thought of as searching a tree, searching the state space tree for a particular goal node, and that goal node is also a leaf node, and dead ends are also leaf nodes. Okay, now let me to move on to the few more terminologies. So each non-leaf node in a tree is a parent that you know. Okay, and each node in the tree other than the root has exactly one parent. Okay, so parent and the children. Okay, this here the trees are represented in horizontal fashion. Usually we are writing the tree in what top to bottom approach also. So parent in the top and children. Okay, so the backtracking, now let me to explain the general algorithm for backtracking. Okay, it is a general algorithm. Okay, not for a particular problem. Okay, but the problems are solved based on this algorithm only. So backtracking is really a very simple. Here we have to explore each and every node of the state space tree as follows. Okay, to explore the node n. Okay, this is the very first step. So see, exploring the node n means making choices in that current stage. Okay, to explore node n, so what we have to do for very first, if n is a goal node, means the node what you are exploring itself is a goal node, then return success. Okay, then return success. If n is a leaf node, then return failure. Okay, so now for each child c of n, what we have to do now means once if there are few more decisions or choices are there to take the decision on node n, and each and every decision will be the child node. Now for each child c of n, again explore the child node. If c was successful, return success. Okay, uh, you have see, this is for loop. The step 3 is a for loop because we have to search it for all the child c of n. Okay, so other once you exit from this, return failure. Okay, so this is what the general plan or general algorithm of backtracking. Okay, if I ask you to explain the concept of backtracking or the explain the general plan of backtracking algorithm, up to year you have to write. Okay, so the concept what I have discussed till now with this algorithm. Okay, now let me to explain the concept of backtracking with two examples. Okay, so the first example is the n queens problem I am going to discuss now. N queens problem, maybe you know this problem maybe. Okay, now let me to explain n queens problem. So first let me to read out the give the problem statement of n queens problem. So here the problem is to place n queens. N queens are there. We want to place all the n queens in the chessboard. Okay, and the chessboard size is n by n. It's a n by n chessboard. So there we have to place n queens. Okay, so that there are some conditions are there. It's not like anywhere you can't place the queens in the chessboard. The conditions are no two queens attack each other by being in the same row or in the same column or in the same diagonal. Is it clear the constraints? Okay, so the more than one queens, two queens should not be placed in the same row or in the same column or in the same diagonal. This is the problem statement. So we have to find a place for all the n queens. Okay, and by satisfying these conditions. Okay, now let me explain one example. See, now I have taken four cross four chessboard. So I can place four queens in this board. Okay, so this is the board what you are observing, and yeah, here I have two solutions here. You can observe here. The two solutions are there to place the four queens. Let me to spend some time on this slide. Okay, so you understand this these two images clearly. Okay, so here one assumption we are making we made here to solve this problem. The assumption is rows are dedicated to queens. Means first row is given for first queen only, second row for second queen, third row for third queen, fourth row for fourth queen. So by dedicating the or by assigning the rows to the queen, one condition is satisfied. What is that condition? Two queens should not attack in the same row. Yeah. So because row one is given only for queen one, first queen. So we can't place second queen in the row one. Second queen should be placed in row two only. Third queen is in row three only. Fourth queen is in row four only. Okay. Hence, so this is one assumption we made while we are solving the problem. And in the right side, you can observe the two solutions. First queen is placed in the second column. Second queen is in the fourth column. Third queen is in the first column, and the fourth queen is in the third column. So now you can observe the very first solution. The queens are not attacked in the same column or in the same row or not even in the same diagonal also. There is one more solution. Is there two solutions are there for four queens problem? The second solution is even you can place the first queen in the third column. Can I place the second queen in the second column? No, I can't place, because if I place a second queen in the second column, it attack with the first queen in the diagonal. Okay, so the best place to place the second queen is first column. Okay, can I place the third queen in the first column? No, not possible, because third queen attack with second queen in the column. Can I place in the second column? No, it attacks with the second queen in the diagonal. Can I place the third queen in the third column? Not possible, because it attacked with the first queen in the same column. So, but I can place the third queen in the fourth column. It's not violating the constraint now. Now search a place for fourth queen. So fourth queen can be placed in the second column. So this is about the problem statement and introduction to the four queens problem. That is n queens. N here is four queens problem. Okay, now this is very beautiful slide, and a very important one. From this slide you are going to understand how the four queens problem is solved, and this is very important one to understand n queens program also. Okay, so now I have designed this slide uh, with lot of effort, because it may be simple, but I need some time to design all these things. But you please, people, make use of this presentation and all these things, then only it is worth. Otherwise it becomes useless. Okay, so now I am going to construct state space tree of four queens problem. Okay, so the very first node is an empty chessboard. Okay, so if it is four queens, take four cross four chessboard. It's a empty board. Now first option, before that let me to repeat the assumption. Rows are dedicated to queens, means first queen is in first row, second queen should be placed in second row, third queen should be placed in third row, and fourth queen should be placed in fourth row. Okay, so now very first choice is, my first decision what I have to take in this stage is Yes. Can I place first queen in the first column? Yes, it is empty. No, I can place. Okay. If I place first queen in the first column, this is the result, partial result. Okay. Now I need to search for place for the second queen. Can I place second queen in the second column? See, now you have to explore the child node. Okay. Now I'm exploring the child. Before that, I verified, can I place second queen in the first column? No, not possible. Because already in the first column, first queen is there. Can I place second queen in the second column? Even it is here also it is not possible. It attack with the first queen in diagonal. Can I place second queen in third column? Yes, I can. So now this node produces another child. Yeah, this is one more child node. Now, so I have placed the second queen in the third column. Now let me explore this child node now. Okay, for the third queen. So you observe here. Now I am searching a place for third queen in first column, not possible. Second column, not possible. Third column, not possible. Fourth column also not possible. Now I have I have used all my choices. Okay, all the choices are over now. I don't have any more choices now. Now this is called as a dead end. So whenever you reach a dead end, what I told you, backtrack, go back to the previous node and change your decision. Okay, yeah, go back to the previous node, and there I already used three choices. My fourth choice is what? What the decision I have taken in the previous node? The decision was I have placed the second queen in the third column. Change the decision now. Place second queen if you have any more choice. Yes, I have one more choice. That is the fourth column. So can I place second queen in the fourth column? Yes, I can place. So it's not violating any constraint. So it produces another node, another child node. Yes, now this is the result. Now we explore this child node to get the solution to the problem. Can I place third queen in first column? Not possible. Second column? Yes, possible. It's not violating any constraints. Yes, I have placed the third queen in the second column. It is one more child node. Now I need to search a place for just for fourth queen. If I got a correct place for fourth queen, yes, I got the solution to the problem. Okay, now I then I can return success. But now let me to verify. Can I place first fourth queen in the first column? Not possible. Second column not possible. Third column also not possible. Fourth column also not possible. Can I now I am going to call this node as a dead end because all the choices are over. Now backtrack to the previous its parent node. What was the decision I have taken in the previous node? The decision was I have placed the decision was I have placed the third queen in the second column. Now you verify. Can I place third queen in the other two choices are left? No. Can I place third queen in the third column? Not possible. Fourth column also it is not possible. These two are dead end. Now these two are not your useful choices. Okay. Now this node I can call this node as a dead end now. All the choices are over. Now what I need to do? Again, backtrack. Go back to the previous node. So when I reach to previous node means the very first child, all the four choices are already used. Okay. Now first child node is also becomes a dead end. Now whenever a node becomes dead end, what I told you, backtrack, go back to previous. Its parent node, make change your decision. What was the very first decision I have taken in the parent node? I have placed first queen in the first column. Now make change the decision means try to place first queen in the second column. Yes, possible. Place it. Yes, okay. Now explore this node. Find a place for second queen. Can I place in the first column? Not possible. It attacks with the first queen in the diagonal. Can I place in the second column? Not possible. It attacks with the first queen in the same column. Third column also not possible. Fourth column, yes, possible. I can place the second queen in the fourth column. Okay, this is the result. Now we explore this result while you are finding a search for place for the third queen. First column possible. In the first column, can I place the third queen? Third queen, yes, I can place. Okay. Second column. Second column. means it's over. For third column, for third queen, I got the solution. Now explore this node. Okay, explore this node to search a solution for fourth queen. Can I place the fourth queen in the first column? No, not possible. Second column, not possible. Third column, yes, I can place fourth queen in the third column. Now, this is the very first solution to the four queens problem. You can observe all the four queens are placed in the in the 4 plus 4 chessboard. Okay, so now this is the one solution for four queens problem. If you want to print another solution, it's very simple. Again, backtrack, change your decision. You can write still you can explore the state space tree, and you will get another solution to the four queens problem. Okay, I hope this method is clear. Okay, the solving this problem using backtracking technique. If you have any doubts, we will discuss those doubts later. Okay, this is about solving four queens problem using backtracking technique. Now let me do explain another example. Okay, another problem. It's a different problem. Subset sum problem. How to solve subset sum problem using backtracking technique. I think it's a new problem for you. Okay. Um, Here the problem statement is okay. Set of positive integers are given. Okay, and one positive integer d is also given. Here I have taken a set a. It contains n positive integers, and one more positive integer d is also given. Now the what we have to make here is we have to generate the subsets such a way that sum of those numbers which are in the subset, each subset, okay, sum should be equals to the positive integer value d. This is what the problem statement, subset sum problem. For example, if a is 1, 2, 5, 6, 8 is set of 5 positive integers and d is given 9. Okay, I can generate 2 to the power of n subsets. No, means here I have 3 plus 5, 3 plus 2, 5, 5 elements are there. 2 to the power of 5 is how much? So 32, correct? Yeah, 32 subsets I can generate. Okay, yes, correct. No, yeah, 32 subsets I can generate. Okay, but here all the subsets are not correct answers. Okay, because when I can decide it's a correct answer, no, when I add the numbers which are present in the subset, the sum should be equals to the d value. The d equals to 9. So now first subset is 1 2 6. 6 plus 2 plus 1 is equals to 9. Yeah, it's correct answer. One more solution is the 1 8. I can add 1 8 also. When I add 1 and 8, answer is again is equals to d. Okay, so these are the two solutions for this problem. I hope the problem statement is clear now. Okay, so let me take one more example. Here I have 1 3 4 5 and d is 11. No, I'm not able to generate any subset, correct subset whose sum is equals to 11. Okay, you can try. Okay, let me take another example. 3 5 6 7 and d equals to 15. So there exists one solution, 3 5 7. When I add 3 5 7, sum is equals to 15. So this is what the problem. For a given set of elements, we have to um, generate the subsets. Okay, so how to solve this problem? Again, using backtracking technique, let me explain how it is solved in the next slide. Okay, so before that, let me to explain a few formula, one or two formulas here which are used in solving this problem. So we are going to record the value of s, the sum of first I numbers in the node. In node itself contains the sum value. If s is equals to d, then it is marked as a solution. Okay, we can either report this result and stop, or we can search for another solution. Okay, if s is not equal to d, we can terminate the node as non promising if any of these two conditions holds good. Okay, what are the two conditions here? Now s is my current sum, plus if I add the next number to that sum, and the total sum if it greater than d, it's no use of continuing that path. It's clear. Current sum is yes. If I add the next number to the current sum, if the total sum, if it exceeding the d value, definitely that sum s is going to be a too large. It is not equals to d. So this is called as a non-promising path. It is not a promising path. Okay, and and if suppose if s is my current sum, if I add all the remaining numbers to s, and the total sum is not it's not equals to d, it's always lesser than d, then again it is a non-promising node, because for the current sum I am adding all the numbers of a given set. Total sum is not, it's always less than d, then it is not possible to get the solution. Then the sum s is too small. Okay, so now let me to give the solution to the problem. So here the problem is a set is given and d is also given. So in the exam also you will get a question like this: set and d is given. You have to consider state space tree like this using backtracking technique. Okay. Now let me explain how this tree is constructed. Okay. It's not an animation. Okay. Just I capture the image from the textbook and I place it here. Okay. So very first node is the root node. Root node, the sum calculated is 0. Okay, so initially the subset sum is 0. Now what I have to do, take one by one element from the given set. First element with 3. Suppose if I add 3 into the subset, then sum becomes 0 plus 3 3. You can observe in the left side of, in the left subtree, the very first child is 3. Why? Current sum is 0 plus 3, it is 3. Now continue this path with 5. If I add 5 to the subset, then the sum becomes 3 plus 5, 8. Take next element 6 with 6. 8 plus 6 is how much? 14. Okay, 14. Still 14 is lesser than 15. Till now it is acting as a promising path. You may get a solution. Okay, but the remaining element is 7. 14 plus 7 is how much? 21. 21 is too large compared to 15. So now I am going to decide this is not a promising path, it is a non-promising path. If you follow this path you will not get a solution. Whenever you reach a non-promising path or a dead end, backtrack, change your decision. What was the decision taken in the previous step? With 6, the decision was, let I have included 6 in the subset. Now change the decision. What is the available decision now? With 6 is over. Now the next decision is without 6. If you're not including 6 in the subset, then the sum remains as 8 only. Now take the next element. 8 plus 7, oh, 15. 15 is equals to d. Yes. Now this is the solution to the given problem. If you want to search few more solution, if exist, you have to continue. You have to construct complete state space tree. Now backtrack, change the decision without 7. Without 7, the sum remains as 8 only, and I don't have no more elements are left in my set. So 8 is less than 15. This is again a non-promising node. Backtrack, go to 8, all the additional choices are over. Backtrack, all the choices are over. Backtrack to 3. Now still one choice is left without 5. If I go without 5, sum remains as 3. For 3, add the next element 6. With 6, 6 plus 3 is 9. And for 9, if I add 7, it becomes 16. 16 is greater than 15. It is again a non-promising solution or non-promising path. Backtrack, I told you, whenever you reach a dead end or a non-promising path, backtrack. Change the decision without 6. So now take the next element, 7 plus 3, it is 10. 10 is lesser than 15 and no more elements are left. Again, it is treated as a non-promising path. Backtrack to 3, all the choices are over. Backtrack to 3, all the choices are over. Backtrack to the root node. Still one choice is left, that is without 3. Go with without 3. Okay, sum remains as 0. Now with 5, it becomes 5. With 6, it becomes 5 plus 6 is 11. And with now for only one element is left, that is 7. 7 plus 11 is 18. It is too large compared to 15. It is also non-promising path. Backtrack. Another choice left is without 6. Now you sum is 5 only. For 5, you add the remaining element 7. 5 plus 7 is 12, which is lesser than 15. So it is again a non-promising path. Backtrack and backtrack to 5 and backtrack to 0. One choice is left, that is without 5. Without 5, sum remains as 0 only. And again, if you explore this, the remaining elements are how much? 6 and 7 are there. 6 and 7 is 13. 0 plus 13 is again, it is lesser than 15. Okay, so no more solution, no other solutions, no more one more solution to this problem. Okay, so the only solution is 3 5 7. So this is what the state space tree to the subset sum problem. Okay, we have constructed this tree using backtracking technique. So in the exam also, if I ask the same question, you have to construct a state space tree like this, and finally uh, you produce the state space tree. Okay, and you can, this state space tree, you can traverse this state space tree in a DFS manner. You have observed, we have considered in DFS manner only. Okay, so that is depth first search, you can find a solution now. Okay, so I hope both the examples and solving these two problems are clear. Okay, so this is what the backtracking technique what I want to discuss in today's class with these two examples. Now let me to stop this sharing. Okay, now it's your time. Now, if you have any doubts, so one by one, you can ask the doubts. Okay, regarding these topics or any previous topics also, or if you want to ask any questions also, you can ask. Okay, yes, come on, one by one. Okay, once your turn is over, please mute your mic. Okay, because others can also ask the doubts. Okay, so I can listen all the queries or issues what you are giving. Yes, come on, one by one. Hello.
ಸರ್ ಅದು
Hmm.
ಹಲೋ ಸರ್ ಈ
Yeah.
ಪ್ರಾಬ್ಲಮ್ ಮಾಡಿದ್ರಲ್ಲ ಸರ್
Yeah.
ಸರ್ ಎಲ್ಲ ಪಾಸಿಬಲ್ ವೇ ಬರೀಲೇಬೇಕಾಗುತ್ತೆ ಸರ್
For which problem? N queens are sum of subsets.
ಸಬ್ಸೆಟ್ ಸಮ್ ಆಫ್
Yeah.
ಸಬ್ಸೆಟ್
Yeah. In the question, if I asked you to construct complete state space tree, you have to construct.
ಓಕೆ ಓಕೆ ಸರ್
Okay. If it is only for one particular solution or for any one solution, you construct only partial state space tree.
ಓಕೆ ಸರ್
Okay. Any more doubts, Shashank?
ನೋ ನೋ ಸರ್ ನೋ ಸರ್ ಲೇಟರ್ ಕಿತ್ತಾಗೆ
Okay. Okay. Yes. Next. Next. Who is going to ask question next? Prajwal? You don't have any doubts, Prajwal? Okay. Rudra Prakash? Rudra Prasad?
No doubt, sir. All clear.
Oh, concept is clear, Rudra Prasad.
Yes, sir. Concept is clear.
Okay, fine. Next. Samrid, in which example you got confused? N queens. Samrid, can you ask the doubt what you have with respect to N queens?
Sir, why we are using without, and if we are adding 3 plus 5, then we are again adding 8 also in that one.
3 plus 5?
Last question, sir, we are adding 3 plus 5 for backtracking, sir, NQ, sir. And
Okay.
we are using one digit more times again.
See, for a particular node, if in the particular node, okay, if you add the next item, next number, if it is a promising path, if it is a promising node, take the next number. Promising path means it may give you the solution. Okay, then take the next number. If it is not able to give the solution, then terminate that path, go back and take again, change the decision, take the next number. So whenever we move to the parents node, its ancestor, then we have to use that number again and again.
Okay, sir.
Okay, next. Yes, Shashank T. Any doubts?
No
Shruti
doubt,
Singh?
sir.
No doubt. Shruti? Shruti Sindhu? Yes, Sonal Singh?
No doubts.
No doubts. Okay. Yeah, I have given sufficient time for you people to ask the doubts. So now let me to talk about this presentation now. Is it okay for you people to understand the concepts, or shall I give the lecture video presentation what I have given till now for the previous topics? I think my question is clear.
Sir, both are comfortable, sir. Whichever you
Okay,
do, we'll understand.
this is this is okay.
Yes, sir. It's okay.
Okay, I think I am going in the correct speed so that you can understand. Correct?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Anyhow, I will present the record also. Okay, the presentation also. Hmm? Okay. Let me just stop recording. Okay, stop recording.